Yes. Now, which one is? Yes.
So good morning, and it's the second day of the conference with Sandra Alves.
So I'm sorry, I start with a disclaimer. I don't really work in linguistics, but I work on proofs, and I work with some with some type systems that are relevant to natural language. This is mathematical linguistics, by the way. Language is formal, language is the other mathematical linguistics. Yeah. So I'm going to talk about structural rules and algebraic of intersecting types. I'm going to look at those appendices in a bit. But first, maybe I'll talk a bit about how I got interested in these things, because this comes from my long-lasting interest in linearity, basically. So when I was doing my PhD, so I might start with not my PhD, my master thesis. So I might start with the last sentence. So my supervisor was working with Wijdamas and looking at an expansion relation between terms that were typable with intersection types and linear terms. And this came from, as an inspiration to previous works by Furi and by Giarelli, Piperno, and Salvo. So Furi, he was the first to first introduce intersection types in a different way, in a way where the intersection type system was aware of the use of resources, and he established that with a linear calculus. And later on, the Carvalho, he established, he highlighted the connection between this type of intersection types, which are called non-idempotent and linear logic. And then the work by Bujarello, Piperno, and Salvo was a relation between intersection types and simple types, in between derivations, typing derivations with intersection types, into typing derivations using simple types. And these derivations, they wanted them to preserve reduction. So that's how I became. So I was working on something else, but my advisor, you come into my office and talk about these things, and I started thinking that these things sounded, fun. So then I did my PhD on that, and I started, and I've been working. I normally say that this is my guilty pleasure research. So that's research that I do because it's fun. Okay, so what do I mean with then looking at the title with structural rules and then with algebraic properties? So in type systems and in logic systems, and we're going to see in why these rules appear, what I mean is a rule for weakening, for exchange, and for contraction. And basically what these rules do is that they, in some way, restrict the way that you can use assumptions. So if you have all of them, then you can say that you're in an unrestricted type system, normal type system. Then if you keep exchange and contraction, you get rid of weakening, then you're in what we call the relevant systems. And in the relevant systems, you are obliged to use always your assumptions. You cannot discard them. Then if you get rid of contraction and keep weakening and exchange, then you're in what it's called normally the affine system, where you can no longer use the same assumption twice, but so you need to use, but you can discard. So you need to use things at most once. And then if you get rid of weakening and contraction and keep exchange, then you're in a linear system. Basically, you have the intersection of the other two. So you have to use things at least once, but you have to use them at the same time, at most once, so that in the end gives you that you need to use everything exactly once. And then if you get rid of all of them, then you're in an ordered system. And then in this case, you have to use your assumptions exactly once and in a particular order.
Are all the other combinations irrelevant?
Yeah, no, I don't know. Actually, that's one of the, you're jumping to my last slide. So that's one of the things that we at some point like explore is what happens if we start just exploring these combinations. What systems do we get? But these are the ones that I'm going to look at today, okay? So then what I mean by algebraic properties of intersection type. So in an intersection type system, unlike the simple types where you need to use every variable function, you need to use it always with the same type. In an intersection type system, you can use the same name, the same variable with different types, and then you need to collect all those types, and normally you then put them together with an intersection operator. And this intersection operator, it can have different properties. It can be associative, commutative, and normally, so the original Computesani system had these three, but like I mentioned already, so the systems like fully the ones that are related with linear logic, they drop the idempotency. Okay, and what I'm going to talk about is a relation where you can drop also commutative, and you can play with these properties. Okay. So what's my language? It's the type of the calculus, which I think we all are familiar with. So we have variables, we have application, and then we have abstractions which correspond to function definition. And of course we have the usual notion of beta reduction that tells you what happens when you put together basically a function and an argument, and that leads to the capture-free substitution, which in the unrestricted lambda calculus you can perform this reduction everywhere then in the term. Okay, so now let's start with our first simple types. So in the simple type system, you can have variables that represent a specific type, and then you can have functional types, which of course represent the types so when you have tau arrow sigma, then this represents the type of function that is expecting something of type tau as an argument and will produce something of type sigma. And as typing environment, we are going to consider a finite list of pairs, and it's important that we use a finite list instead of a set, because the set is going to ignore exactly the structural aspects of the proof. So we do want to deal with assumptions as a list, and it's a list of pairs x tau where all the term variables are distinct. Okay, so in a typing environment in the simple type system, I can only have one assumption for each variable. And a typing system is going to be something of this form, and which means that if I take the assumption in gamma, then I can assign the type sigma to the term A. Okay, so let's look at the rules, what are called the logical rules first. So this is also, I'm sure, very familiar. So if so I have the rule for the axiom, which states that if I assume that x is of type tau, then I can, conclude that x is of type tau. And then I have the rule for the arrow introduction, type abstractions, and then I have the rule for the arrow elimination to type applications. And when I have an application, of course, there needs to be, is there a pointer? No, yeah. There needs to be a match between the type here of the expected argument and the actual argument that I give to the function. So there are some things that we can look at here, which is, for example, when I type the axiom, I'm not allowing for extra assumptions to be here. Okay, so I only have one assumption. Okay, and then when I type the abstraction, the function, I'm assuming that when I type the body of the function, there is an assumption there for the argument. Okay, but if we think about it, since we are only allowing when I type, so this assumption was not introduced by an axiom rule. It cannot be introduced by an axiom rule if the parameter does not occur in the body of the function. So if the parameter does not occur in the body of the function, then this assumption needs to appear somewhere. And also, I'm assuming that this assumption is because remember that this is a list, not a set. So I'm assuming that this assumption not only exists, but is to the right of all the other assumptions. Okay.
So, which means that you don't allow redundant abstraction, right?
Well, then I will allow it with the substructural rules. Yeah. And then when I type an application, then there will be a list of assumptions coming from the function. I don't think the batteries are very good. Okay. So there will be a list, gamma 1 of assumptions coming from the function and a list of assumptions coming from the argument, and then we'll just put them together. We will concatenate these two lists. So this will also have like a particular order. Okay, so of course, then if we restrict this, we need extra rules to do what we, if I want to have extra, I want to change the order of assumptions. But otherwise, we wouldn't be able to type all the types that we are expecting to type in a single number system. So that's why we then have the structural rules. So the structural rules are basically like the bureaucratic rules that deal with the structure of my set of assumptions. So I have a rule for weakening to allow, for example, if I have a function parameter that does not occur in the body of the function, then this is how I then introduce this assumption. And I can introduce it anywhere in the set, in the list of assumptions, in any position. Then because when I use the application rule, I just concatenate things, so there's a specific order, but then when I abstract, I'm expecting the argument to be on the right of all the other assumptions. So then I need a rule to swap assumptions.
But I guess the variable x may not occur in gamma 1 and gamma 2.
Yeah, no, because as I said, I'm assuming that so I define a type assumption, and I always assume that if I put these two things together, then any variable occurs only once. And of course, if I add this x here, then this x needs to be something that didn't occur yet. Because I'm assuming that in a set of assumptions, each variable occurs exactly once, okay? Only once. Okay, so the exchange rule, it will allow me to swap between two assumptions. And then the contraction rule. And this contraction rule, it works almost like, so we are going to talk a bit about linearization in a little while, when we get to the intersection with the relation with intersection types. And this works a bit like, if you look at the proof from bottom up, it's like you're doing linearization, going from the conclusion to the premises. So basically, the thing is that point, I assume that I was using, these two names with the same type, then I can collapse them in the same name. Okay? Because this is the way that I need to do this. Well, this is a choice for the contraction rule, which works, for example, for what I want to do, because I want to relate this with linear systems. So I will start. We'll see some typings, in a bit. So I will start with basically, if I want to have an f that occurs twice, I will start basically with two f's with different names, and then I will make them one when I put the set of assumptions, the list of assumptions together, okay? And I will rename the two to be just one. Okay.
We like reflexivity.
I didn't think about it like that. Okay, so let's look at some examples. So, for example, if I want to type this term, then if you look there, you have this function which, the x occurs in the body of the function, but then the y doesn't. Okay? So that y will need to appear, and so not going to appear by the axiom rule. So from the axiom rule, I can conclude that x is of type alpha arrow alpha if I assume that x is of type alpha arrow alpha. But then now, because I want to abstract y, I need to add an assumption for y. And I will add the assumption that y is of type beta. Then, so here I'm using the Whitney rule. So then we can abstract the y, then we can abstract the x, and then we can type the identity function as expected, and then we can choose the rule, and we can type this term using the Whitney. Okay. So now, if I want to type this term, so in this case, what happens is that if I start typing the body of the function, I have y applied to x. So I will start by typing y with type alpha arrow beta, and then x with type alpha. Then I use the application rule. But now, see, I want to abstract y first, but the assumptions are not in the order that I want, because I want the assumption for the variable that I'm going to abstract to be on the right, and it's not, it's on the left. So this means I will have to use the exchange rule and swap these assumptions, and then of course I can abstract the y and then the x. So to type this sort of terms, I need to exchange. And then for a use of the contraction rule, so in this case, I want to type this term here, which corresponds to the rule 2. So I have two occurrences of f. So I will start by using, like I said, different names for this f. Okay? Because when I put together the two sides of the application, for the left hand side of my sequence to be valid, I can't have twice the same name for a variable. So that's why we start by using different names. So I'll assume that f1, they of course have to have the same type, because we are in simple types. So if I have f1 of type alpha to alpha, then I can conclude that f1 is type alpha to alpha, and then on this side, I will assume that f2 is of type alpha to alpha, and conclude that f2 is of type alpha to alpha. Then I assume the type alpha for x, then f2 applied to x is of type alpha, and then f1 applied to f2 of type x is applied to alpha. And now I have here the two f's, and they have the same type. So then I can apply the contraction rule, and so I'll get f applied to f of X with it's of type alpha, and now I only have here one assumption for F, okay? And then I can abstract, and I'll get the type of the church rule too. Okay. Okay. Of course, that I mean, if you don't consider that environments are lists, then you don't need to have these rules. But you're hiding. I mean, there are lots of details about the structure that you're not being aware of. So, and even if you consider, so what I gave you this logical rules and these structural rules, they type simple types, but they are not expressive enough to to reason about the different restricted uses of my assumptions. Okay, so in the type derivations that we see, we can erase, we can swap the order of things, we can duplicate. So now we want to look at systems where we are going to be more restricted. Okay, so these are the substructural systems. So I'm interested now in removing, like I showed in that table in the beginning, removing one or more of these structural rules and seeing what system I get. So these substructural type systems, they of course are related to what are called substructural logics. And so we are going to look at the linear and the order and the affine and the relevant, and they're connected with linear logic, which of course is very important for any system where I want to be resource aware, and the order system is connected to Lambda order logic, and this is where my work is somewhat relevant to this event. And then of course if you look at relevant system, then this is connected with relevant logic. Okay, so let's start with the relevant. So as I said in the beginning, let's get rid of the weakening. So we keep the exchange and the contraction, but now we are no longer able to introduce an assumption for a name that does not appear in the body of the function. Okay? So this means that if I type term, it needs to be a lambda-ite. So it needs to be a term where in every occurrence of an abstraction, then the parameter needs to appear in the body of the function. Okay. So, for example, the term lambda yx is not typable in the relevant system, because to type that term, like we saw in the example, we need the weakening rule, but we can still type these two terms, that the S combinator and the number, because we have exchange and we have contraction. So then let's look at the affine system. So in the affine system, we are going to get rid of contraction and keep the other two. So we have weakening and we have exchange, but we no longer have contraction. So this means that because I have the restriction that my typing environment always needs to have only one assumption for each variable, then each variable can only occur once in the term. Okay. So in this case, we can type the identity, we can type the lambda xy, which we couldn't type before because now we have weakening, but we can no longer type the S combinator, and we can no longer type the church rule too. And then if we get rid of both weakening and contraction and we just keep exchange, then we have the linear system like we saw in the beginning. Here we want to restrict the use of assumptions in a way that I use each assumption exactly once. So now it's like we put the two restrictions together. So because we don't have weakening and we don't have contraction, then for each subterm of the form lambda x, and then this x needs to occur free in n exactly once, and then each free variable has to occur just once. Okay, so this means that it has to occur exactly once if you put two conditions together. So now we can type the identity, we can type that term that the example that we saw where we swap the order of the assumptions, but we cannot type the lambda x y or the church number 2. And this is a system. So I mean, every time that you have don't have weakening, then you will have both subject reduction and subject expansion in this restriction of simple types, but you don't have subject expansion whenever you get rid of weakening. Okay, and the last one is we get rid of all the substructural the structural rules, and in this case we get the ordered system. And for the ordered system, we need to change the system a little bit. Okay, so our axiom rule is the same, but now whenever we have an abstraction, we are going to consider two cases. We're going to consider the case where the parameter is to the left, and in this case we are going to annotate the arrow with an L, and we are going to assume the case where the parameter is to the right, and in this case we are going to annotate this arrow with an R. Okay, and then of course if we have these two rules for the arrow introduction, then we'll have two rules for the arrow elimination. This one which corresponds to what we are used to seeing. So if here I'm assuming that the argument is coming from the right, then when I put together the two lists of assumptions, I will just concatenate them. But in this case, I will concatenate them, but I will swap the orders. So it's grammatically before.
Real grammar still allowed outside.
So this case, in this system, we don't have contraction. So this is a linear system, and also we don't have weakening. So this is a relevant system, and also we don't have extension. We don't have any structural rule. So the order of the assumptions is important. So is this term typable in the order type system? Well, the answer is yes. And in fact, you have two different ways of typing it. And in some way, if you relate this system, because there's also everything that's typable in the linear system is going to be typable in the ordered system. But there are some typings in the some ways of swapping that you can do in the linear system that you cannot do in the ordered system. So in the ordered system, you have these two typings that are valid, okay? But these two, for example, are not valid, okay? So if you consider this list of assumptions where you say that Z1 is an error type with annotated with an R, but then the argument of this function is going to be Z2, which is on the left, then we cannot type this with the ordered system, and the same way with this. Okay, so now let's go to the other side. So we talked about structural rules at this point. So now let's do like the slide detour and talk about intersection types, and then we come back and bring these two things together. Okay. Okay, what are intersection types? So intersection types they appeared in the 80s, and they are a characterization of what are strongly normalizable terms, in the sense that everything that is typable with if a term is typable with an intersection type, then is strongly normalizable terms. So every reduction sequence ends in a normal form, and of course, because of that, these type systems are not decidable, but they have restrictions that are interesting, and there are reason about all sorts of things, and in particular, so like I said, in the intersection type systems, we can, for a variable, unlike the simple type systems, for a variable, we can use different assumptions for the same name, which then we put together using this this operator, and of course, if a term, because all the terms in the simple type system are also normalizable. So if a term is typable in the simple type system, then it will also be typable in an intersection type. But there are simple types are not enough to characterize normalization, in the sense that you have terms that are normalizable, but that you cannot type using a simple type. So, for example, if you consider this term here, lambda x, and then the self application itself is not typable using simple types, even though it's a normal form. Okay, let's look at the set of rules. So you have, again, a relevant axiom rule, but now this tau is an intersection type. Okay? It's not an intersection of types, it's an intersection type. Okay? I should have put a slide with the set of types, but basically, I mean, you'll have, again, you start from simple types, and then you have types. You build them in this way. So you have arrows where on the left hand side you can have an intersection of types. Okay? And these are not necessarily simple, so they can again be the types that are expecting an intersection of types and return type. So the idea is that in this presentation of the system, I don't have an intersection of types as a type for something, right? And this is normal. Sometimes there are some systems where you can add that, but that's basically more just to make proofs easier. Okay, so the idea is that then you have, again, the axiom rule, which is a relevant rule in this case. Then when you type the function, then you type the bottom of the function with the type sigma, and then you will have an assumption. And here I'm using sets because here I'm not interested in the structure. So here you have for x, you can have an intersection of types, okay? And this intersection is not empty, right? Because if this intersection is empty, then there are systems where you can consider this intersection to be empty, but in that case, then you can type things that are not strongly, or type exactly strongly normalizable terms, then this intersection cannot end. Okay, so if you have this X with this intersection of types, then you abstract and you get this type. But of course, again, because we now need to have the weakening in some way, because here I'm assuming that if this is not empty, it's because the X occurred at some point when now in M. So then this is why this rule is called intro I, okay? Because it's when you have a term where the parameter occurs in the function, but then you have another rule for the case where it doesn't. And in that case, I will just pick a type here. Okay? It can be any type. Of course, when I type then the application, the argument needs to have this type, and this is why then I have characterization of strong normalization. And of course, then when we have the application, so I will have a function which now has a type of this form. It can be just one, but not zero, like I said. And then in this case, I will need to type the argument with all the possible types that I have for my parameter. And then we are just going to consider this conjunction of all the bases, which basically is going to put together whenever a variable occurs in more than one of these gamma I, then it's going to collect those assumptions and put them together with an intersection operator. Okay. Okay. So now we can type this term lambda x applied to x. Okay. So because I now can assume that x is of type alpha arrow beta, and at the same time I can assume that x is of type alpha, then I can type the self-application with type beta, and I put together the two assumptions for x, and then we can abstract that, get this type for this term, which is normally called delta. So here's how all these systems relate, and I'm relating them in a way that, so every term that you can type with the ordered is typed with the linear. And of course, like I said, also every term that you can type with the linear, you can also type with the ordered. But in some sense, the linear has more like possible typings for the same term than the ordered. So that's why I wrote this as a hierarchy. There's no relation between the affine and the relevant in an order. Okay. So now let's put these things together. So what is the relation that I want to talk about here? So this relation is going to be in terms of what Florido and Damas define as the expansion relation. So if you consider this term which we saw is typed with intersection types, so it's the delta type. The delta term applied with the identity. So this is an identity. Okay. So to type this, what we need to do is we need to type the delta term with this type here. Okay. So this intersection of alpha arrow alpha arrow alpha arrow alpha, and this corresponds to the first occurrence of x, because both of these occurrences of x, when I reduce this term, are going to get identity functions. But because the first one is also going to get the second as an argument, then the type of the first one needs to be something that's also expecting an identity as a parameter. So the first occurrence of x has this type, and the second occurrence of x has type alpha arrow alpha, and then type alpha arrow alpha. And we can expand this to a linear term where we consider now, instead of two occurrences of x, we rename these occurrences. We have an x1 and x2, and then of course, because we have these two variables, we abstract them. So now, instead of a function that takes a parameter and uses that parameter twice, I'll have two linear functions, and each time each parameter is used exactly once. But yeah, because now I had only one parameter, and now I'm abstracting twice, so then I need to give enough arguments. So I need to make a copy of the argument. So this is what we normally call linearization. So basically what we did is we expanded this term to a linear version here, okay, which has the same type and which is typable in a linear system, okay. So now I don't need intersections to type this term. I can type it using the linear system. Okay, so this is done, like I said, using this notion of expansion. And I'm going to start with what is called the ACI expansion. Okay, ACI in the sense that the intersection is associative, commutative, and idempotent. Okay, so in this case, what we do is when we have a variable, and we define this expansion on typing. So a term together with a type, okay? So if I have this, and this is a relation, if I have this x is of type tau, then I'll just return y. So I'll just give a variable that's different from x, and I will make like I will record that in this what is called this example. Means that this variable expands to this one with this type. And then when we have an abstraction where we have an intersection of types on the left, then if x occurs in the body of the function, then I will, and I can expand and I can have different expansions, but I can expand this m to a term, m star, and then I have this expansion context where x is going to be mapped to different variables, x1, xn, okay, with these types corresponding to all these different types that I have here. Then I will abstract on those variables over m star. Okay. And then I'll have again a limit for when the variable does not occur in the body of the function. And in this case, I'll just then put a fresh variable and after expanding the body of the function. And then if we have an application, then we can expand if for some k and for some list of tau types, tau1, tau k, I can expand the term m with this type, and then I will have to expand this argument n using the different types that I was there. Okay, and then we put the expansion context together. And what basically this operation does is going to collect all the expansion variables for the same name. So for example, if we look at this term that we linearized before, so I can, for example, here expand this x into x1, and I will record here that x is expanded to x1, and then I can expand x again to x2, and then I record that x is expanded to x2, and then using the application rule, I can just put these two together, and now I know that I have that x was expanded to x1, x2, and then we use the abstraction rule, and we get that this lambda x with this type is expanded to lambda x1, x2, x1, x2, and now because I have abstracted the expansion context is empty, and then we can easily expand the identity to both to always to 1 the ZZ. We can do it. We can expand it in the same way, like I said, with a relation. We could have used different names, so then I can put everything together, and I get this, which was the the term that I showed you that we could obtain by linearization in some way. Okay. But of course, I can do another something else. I can just expand. This is now for this number 2. Okay, so I can expand F to F1 with that type, and then X to X1, and then I will use the application. But then now, when I expand again F, I can use the same variable and the same variable. So then when I put the 2 things together using the application, then I will have here, because I'm considering intersection that is idempotent, so the 2 occurrences of F1 can collapse. Okay, so basically I can get basically the same term but renamed with different variables. Okay, so this is not really linear. It doesn't guarantee that I get something that has been like linearized. For that, we need to get rid of something else. Okay, so but we have properties that relate this expansion with a system. So let's see which system. So first, we're going to consider this transformation, which kind of occurring between intersection types and types. So for type variables, it's just going to give you the same type variable. And then when I have an arrow type where on the left I have possibly an intersection of types, then I'm going to transform this into arrows. This is to transform an intersection type into a simple type. And if I have the expansion, the ACI expansion, so I have here a term M with the type sigma that is expanded to N and an expansion context A, then I have these 2 properties. So if M is typable in the intersection type system with type sigma, then if I apply this transformation to both the assumptions in gamma and to the type sigma, then the expanded term is typable with the simple type system. Okay? And if it's a lambda I term, then it's even more restricted. It will be typable with the relative type system. Okay. Okay, so now let's consider that our intersection is associative, commutative, but it's not idempotent. So what this means is that when I have an intersection of tau with tau, I want this to be different from tau. So I want to remember that I use the same variable twice. Not only that, because when you consider that the intersection is idempotent, basically you have a qualitative use of types. You want to remember in the different ways, of the different meanings for a specific variable. You want to remember that you can use that variable with different types, but you're not interested in remembering how many times you use that variable. But once you get rid of the idempotency, you're also remembering how many times you use each one of them. So when we were considering ACI, remember that we expanded this to a variable, which I only wanted it to be different from X. Okay, and now I want a bit more. I want it to be a completely fresh variable. Okay. and the rest of the rules are the same. Okay, so the only thing that we're going to change is this rule for the variable. Okay, so in this case, when we expand, for example, this term here, then in the end we are going to have exactly three different variables. Okay? Actually, here I have expanded, so this shouldn't be in the expansion context anymore. Okay? So this should be in the expansion context before I expand, before I abstract from the x1 x. But the idea is that, for example, if you remember when we did the expansion for the number 2, that we could still have the number 2, not a linear version. But now we will get a linear version of the number 2. Okay, so get a bit faster. So in one property that we have in this expansion is, like I said, that the number of types in the intersection is exactly the same as the number of the free occurrences of the parameter in the function body. And of course, we have some properties for this this expansion. So if I now use this expansion and for a term m with type sigma, I expand n and a context C, then if this term is typeable in the intersection type system, then, and here I'm using the same transformation for the types, then the expanded term is going to at least be typeable in the affine type system. But moreover, if it's a lambda I term, then it's going to be typeable in the linear system. Okay? And then we can get rid of so we can, in this case, we consider the A expansion, where we have that's the intersection is associative but no longer commutative nor added. And in this case, I'm showing so these rules are a bit heavy, and I'm showing the rules. I'm not showing the rule for the variable, but the rule for the variable is the same as for the case of AC, but we annotate the variable with a current type, or the current type. And in this case, so when I now have this intersection here, I will expand the body of the function, and this will give me an expansion. And in this case, this now is a list, okay? And this expansion of this variable is on the right. So then I will annotate all these arrows with an R. And I can also have the expansion giving me an expansion context where this X appears on the left. And in this case, I will annotate this term with else. And then I will have two rules for the application. One where I will have here this annotated with R's. And in this case, when I put together the expansion context, I will keep the order. And then another rule where they are annotated with else. And in this case, I will invert the order of the expansion context. Okay. So in this case, if we consider, for example, this term there, which is basically an unlinearized version of the term that I showed you that was typeable in the order type system, then I can expand this starting with x1 with this arrow type annotated with an R, and then I expand Z, then I put them together, and now because the X is on the left when we expand, we are going to annotate this arrow with an L, and then expand the parameter, and then we put the two things together, and this will give me the one of the typings that I showed you. I could get the other one, but then that means that I would need to start with a different annotation for the first X there. Okay. So what are the properties of this ordered expansion? So if I have here that I can expand M with type sigma to N with type tau of T of sigma and an expansion to A, then, and in this case, of course, M needs to be a lambda I term because otherwise I cannot expand it. It would not an ordered term. Then I will be able to type this in the order type system, but then this transformation is a bit different because it needs to go from intersection types to order types. So in the case of variables, it's the same, and in the case of intersections, well, I'm going to annotate them with R's, but I could choose to annotate with L's, or I could even have like a mixture of them, but then that would give me, different typings and different results of expansion. Okay. Now, what about reduction? So first, let's consider what is called weak head reduction, which is, so remember the beta reduction that I said that in the unrestricted lambda calculus you can do everywhere. You can reduce everywhere in the term. When we consider weak reduction, or in this case, weak head reduction, we are going to reduce functions only at the head position of the term, and we are not going to reduce inside functions. So this is an interesting reduction strategy because if you think about functional programming languages, reduction is weak, so you don't really reduce inside a function. If the result is a function, I'm not interested in computing its body. And one thing that we have shown is that if we consider weak head reduction, then all the expansions that I showed you, they preserve reduction in the sense that if I expand, if I reduce a term using one step of weak head reduction, then the result of expanding the initial term will reduce in possibly more steps to the result of expanding the second. So for the case of beta reduction, we still have this also unrestricted reduction. We still have the same result if we consider the lambda I, but we don't no longer have this result if we consider the lambda k. Okay. So, for example, so if we erase, then we no longer commute with beta reduction. For example, this term here, because if I do a step of reduction here, I'm going to erase this x here, and this abstraction is going to disappear. But if I expand, because I have these two occurrences here, then this is going to give me, or possibly I can expand to this term here, both using the AC, any of them, but then I can't get from this term to this by expansion. Right? Okay, so to conclude, if I consider the ACI or the intersection, and I consider as the source the unrestricted lambda calculus, then I'm guaranteed to, or I can get a term that is typable in simple types, and which preserves weak head reduction. If I consider the lambda I and still in the ACI, then my target system is the relevant system, and I'm guaranteed to preserve also the reduction. Then I look at these two together. Then for the AC, again, I can consider the unrestricted lambda calculus. And in that case, I'm guaranteed to type with the fine types and preserve with head reduction. And moreover, if it's the lambda I calculus, then I know that I can the terms that I obtain by expansion are typed with linear types, and I can preserve with the reduction. And for the order type, I only consider lambda I because otherwise, no, I can't type it using an ordered system. And in that case, the expanded term is typed using ordered types, and I can observe the reduction. And so how these structural rules relate to the different expansion relations. So the ACI intersection is related to the relevant system, where I have expansion and contraction weakening. Then the AC, we can relate it to either the affine, if I consider the unrestricted lambda calculus, or the linear, if I consider the I, and then the A is related to the other type system. And what are we, what are we currently looking at for a long time? Because like I said, this is something, it's like because it's a guilty pleasure research, I only do it from time to time. So remember that we had these two valid typings, but there were some that were not valid. There were some exchanges that I couldn't do. So what we would like to do is like have a notion of type. Well, an algorithm that would, instead of putting there an R and an L, it would put like a variable, label variable, that then when I replace that variable, it will give me the possible typings in the order type system. But of course, the thing is that this becomes very bureaucratic very quickly, because in some way I need to get this algorithm, I need to play with the structure of the environment. So I need to, if I use a particular variable, then I will have to apply that also to the basis in a way that if I choose that to be, for example, an L, then I will have to swap the two things in the end. Okay. And also we would like to look at first the relation between the linear and the ordered system, explore that relation more. And like, in the beginning we talked about is, what about the other substructural system? Are there, is there any other system left that's interesting? What happens if I start just combining these properties? And what expansion relations also can I get? And I think that's it. Thank you.
Questions?
Maybe categorical grammar. Oh, they'll say about left and right applications. Because categorical grammar they allow. Right?
Well, I don't know. I mean, so I decided, like I said, I don't work in linguistics or natural language processing, but I do find it very interesting.
Formal language.
Yeah, and so when I saw that this conference was taking place, I said, "Oh, I'm going to attend this conference," and then it was like,
Very important actually is the typing. Probably I don't know, say more, because they'll give more examples about. You mentioned yesterday the lexical entries that are ambiguous with respect to their type. Some are verbs, others are can is a verb, or No. So then the types are completely. So polymorphism is important. It is, I think, is important.
Yeah. So the idea that what we want to have is a kind of polymorphic version of this. But the thing is that I thought we have a version of the algorithm which works with the examples that we looked at, but then we were trying to of course prove that the algorithm was sound and lead, and then it wasn't that easy. So now we are, because to make it, we're trying to do one intermediate step. So have a system where we have like polymorphic order type, and then try to relate the order type with that one, and then that one with the
I have a very general question, maybe a bit irrelevant. So, but there is one type system where the ordering comes in naturally, which is if you have dependent types, and you have a dependent typed context, then the dependencies define, kind of determine the order that you cannot swap. So, is there any relation to this?
Well, I haven't looked at that, but yeah, but
But you see what I mean. So if X is of type A and X1 is of type A and X2 is of type B, depending on X1 and so on. So then there is no way you can reorder the context.
But it's only a pre-order.
Yeah, so it is an order, but then it's under some conditions you can swap them.
Yeah.
But if there is no dependencies, so actually it's a different. It's yet another different.
But there is a way to get around this. I think it's probably related. If we go to page, I think 41 or something, I think it's related to. Because there you actually are creating the intersection types. They create here somewhere. One. Even the slide with very abstract. When you have, yes, somewhere here. Yes. So actually, am I right that this actually determines the order and the types. So the first argument, the second and argument. Independent types, imper-Martinov types, they come in specific.
Of course, in this case, in this expansion, I could, before doing this, I can of course, swap them, whereas in the order I can't. Yeah.
Then here, situated dependent type theory will come. We go to such a question. So here, this is for total relation. And if we are working with partial relations, so some of the arguments there allow filling up the argument role. So actually you are coding here the characteristic function of an n-place relation, n+1 relation actually. Then at ith place, ith argument allows to insert objects, names, terms for some object, and then the characteristic function is not defined. And with the coding, then it's not known. You lose information what is undefined, whether the characteristic function the relation is not defined on ith place, or at the end the value of everything is defined, and at the end you don't get for these arguments for the tuple of n and argument n object, then the function is not defined. So that was one of the motivations for situation theory, this partiality to allow, because natural language allows undefined values, etc. And also in general recursion theory also allow undefined partial functions, relations. So that was the idea, to allow partiality. So when we say partial relational type theory for natural language, that's two ways: partiality with respect to these partial relations where there is no value, and then the Turing machine, we never know how long wait wait for a value, or it's undecidable. Or small possible worlds with only a little bit information in them. So partiality comes in many aspects, then in many ways. And here, actually, and also here the order. So in situation theory, so Barbais and Etchemendy, they laid out philosophical grounds of situation theory, and I grabbed all those ideas and I made mathematical structure. Okay. And then here, one way, in mathematics, we are trained functions and argument function. The order of the arguments is fixed. We choose one of them. So plus, it's index of, they come in a specific order. Multiplication, it comes specific division. But in nature, somehow, there's no. So this is artificial artifact versus mathematics is very powerful with the coding.
Yeah, so I think this takes us to different topic. So we have a question.
Yes.
Another question.
Yeah.
Okay, so I think you mentioned this slightly in a talk, but instead of treating intersection as an independent type, this treatment seems to restrict the possible appearance of the intersection types in the proof diagram. So, what is the advantage of that simplification or the restriction, the intersection types?
What is the advantage of
Not just adding intersection type, but the inventory of types, but you integrate it into the type systems. And well, correct me if I'm wrong, but it's looks to me that intersection type cannot appear everywhere where the ordinary type can appear.
you mean in the intersections? You're referring to where the intersections can appear?
Yeah. And what is the advantage of that restriction?
Oh, that I only consider the intersections as at the left arrows, basically.
Yeah.
Well, I mean, they can appear at the right of arrows, but then again, but not as a result. Okay, so basically, I mean, you can have a system, and for example, normally when I work with in other words, when I work with intersection type systems, then normally we distinguish derivation that ends with a type, then a derivation that ends with and most of the work that I've done using intersection has been with non-idempotent intersections, so derivations that end with a multi-type, which is basically a collection of types. But the idea is that we think that in terms of, like, if you think of computation, then you want the results to be a type, the multi-type. So you consider the multi-type as the type of the parameter. So basically, when you use something in a function, then you can use it with as a set of types or a sequence of types, but then you want your result to be of a single type.
So that leads me to my second question. That what about the combination of this thing with a product type? Do you allow product like A times intersection something.
Well, yeah, I guess you can have, I mean, if you can use, for example, if you have, you want to work with pairs or something like that, yes, you can find this thing. I have some work with that's related to quantitative analysis of pair pattern calculus, and there you can have that.
Thank you very much.
So maybe do this question.
You have another question?
Yes. So maybe both of you can give us examples for languages where, you know, the verb comes at the beginning, subject, verb, subject, object. And I think then this will be probably relevant for such examples in the surface syntax.
Questions in Swedish.
Hmm?
The last question in Swedish.
Oh, okay. Two questions there. But then for the, if you are asking question in Swedish for a specific item, how do you ask the question? What do you put there? So it will be always the verb, and then the arguments will come from the right. You apply the right application. And at a certain point, it will be empty. Because you have this question and somebody fill up. That's my hallucination, right?
Okay, so.
So, thank you for the talk. How I wanted to know how to think about intersection types. Like, is there an introduction rule for intersection types, for a term of having type tau and tau? For example, product types, we can think of them as
So let me go to the type system. So I gave this presentation of the intersection type system, but instead of, for example, instead of having this rule here where now I have here n typings for this n, there are systems where I can in fact introduce this intersection, so I can from all these derivations, then I can introduce an intersection with all of them, and then basically the application rule looks like the normal application. Okay? For in terms of because I said that this is a characterization, this typing system characterizes exactly strongly normalizing terms. So in terms of characterization, that doesn't change. Right? So normally, sometimes you use that presentation because it might make proofs easier, but you don't really need to do it like that. So instead of, in this case, I never have a sequence that ends with an intersection. And then, of course, when I want to type an application, I need to have all these typings for the argument. I'm not sure if I answered the question.
Yeah, I think. Yeah.
There is no introduction rule for intersection.
Yeah, there's no introduction rule for intersection. Yeah.
We have 20 minutes.
We can also discuss at the coffees.
Coffee. Yeah.
No, you need to come. Okay. Thanks.
Just tell me this. I just put other language allows.
Many languages come from different words.
Well, it is quite
To change
clear.
the
I don't know how you stop the recording.
Bulgarian is quite free. Free orders. Ivan